Hello everyone. In this video, we'll be talking about the demodulation of AM wave. In the previous video, we have seen the production of AM wave. We take up a message signal and a carrier signal and we do the amplitude modulation. And then this wave is fed to some power amplifier which boosts the power, and then using the antenna of appropriate size, the AM wave is transmitted. You remember that? Now we will be observing the receiving process of the AM wave, and then finally we'll be taking out the message signal. Got it? So for that we will see a block diagram on the screen. First of all, you can see a receiving antenna. This antenna receives the AM signal, and while receiving the AM signal, it might got attuned because it has traveled through the channel. So the next stage is an amplifier which boosts the power of the signal. After that, there is IF stage. In the IF stage, means intermediate frequency stage, the carrier signal's frequency is decreased. Okay. And then there is an envelope detector. This envelope detector can be a simple RC circuit or more complex circuits also. In this video, we'll talk about a simple RC circuit. This envelope detector's output is giving you the message signal. Again, this is amplified and then sent to the final output. Got it? In this way, we can obtain the message signal. I am showing you another block diagram so you'll get the better idea, and then we'll discuss the details. Here in the left hand side, we can see an AM signal. This AM signal is passed through a rectifier, half wave rectifier. Then we got only the positive cycles of the wave, and then it is fed to the RC envelope detector, and then we obtain the message signal. Got the simple process? Now we'll see the detection of AM wave. Pay attention. Here we have an AM signal. Okay. This AM signal is passed through a diode. We know that diode conducts if and only if it is forward biased. It means this positive half cycle will only appear on this side. Means I can delete this part of the AM signal. Now we'll focus on this part. When this cycle is attaining its peak, let's say the voltage level reaches up to here. Since the voltage is positive, so the diode is conducting, so the capacitor will get charged. So the output across the capacitor I'll indicate with the red marker. Let's say capacitor get charged to a voltage Vc. After this moment of time, the carrier voltage is dropping down, the AM signal's voltage is dropping down, but the capacitor's voltage is greater than the AM signal's voltage. For example, what I mean to say, suppose the AM signal's voltage level reaches here at this point, but capacitor has been charged up to this level. It means the voltage across capacitor is more. Just for example, suppose Vc is 10 volt, and at this point the voltage of the AM signal is 8 volt. It means here we have 10 volt and here we have 8 volt. Now check about this diode. Is it forward bias or reverse bias? Now the diode is reverse bias because the P side of the diode is connected to the lower potential and N side of the diode is connected to the higher potential. It means now the diode is switched off. For this black line of the AM signal, the diode is switched off. When the diode is switched off, the capacitor will discharge through the resistor. Okay. When capacitor is discharging, its voltage will fall a little bit and let's say reaches up to this level. The red is indicating the voltage across the capacitor. Okay. Now, again, there is the positive cycle of the AM wave. So, this capacitor will get charged up to this value and then the same drama repeats. As the voltage of the AM signal falls below this peak value, the capacitor will again discharge, and then again capacitor will charge, then again discharge, and this will keep on happening. If you check this output across the capacitor, it will resemble to the message signal MT. Got it? Now, in the original derivation, if you remember, we took that frequency of the carrier wave should be very high. Think about it. If the frequency of carrier wave is very high, it means these lines will be very close. Do you understand? Frequency is very high means time period is very small. Time period is very small means the cycle will be completed in a smaller amount of time. Just imagine these lines are very close. If these lines are very close, then these ripples, by ripples I mean this thing, it's going down here, it's going down here, going down here. If the lines are very close, these ripples will be small. Do you agree? And if these ripples are small, then the signal will, this voltage across the capacitor will resemble with the MT, will be almost identical to MT, the message signal. Do you get this? I'll give you another illustration so you get the better idea. Suppose this is another AM signal. Okay. And in this AM signal, the carrier frequency is very less. Capacitor gets charged here, then capacitor gets discharged, then capacitor gets charged, and then capacitor gets discharged. This voltage across the capacitor, is it following the message signal? The shape of the envelope gives you the idea about the message signal. Now you can check for this kind of configuration, the voltage across the capacitor will not follow the message signal. On the other side, if we have a signal like this, just pay attention, where the lines are pretty close. Just to give you the idea, I'm drawing it quick. Lines are close means the time period is very less. Okay. Computer generated diagrams will be much better, but you'll get the feel. Now the capacitor gets charged and then discharge, charge, discharge, charge, discharge. That will keep on happening, and you can check this thing that this time the ripples will be almost negligible. So you'll get the better recovery of the message signal. Understood it? So here is a condition for the better recovery of the message signal. The RC should be much less than 1 by bandwidth of the message signal or the modulating signal or the information, you can call anything, and here I should write 1 by FC. Got it? I'm explaining the condition again. The time constant of this RC circuit should be greater than the time period of the carrier wave, because while the capacitor is getting discharged, this voltage level across the capacitor should not fall too much. If the voltage level across the capacitor falls too much, then there will be a great ripple. So the 1 by FC must be much less than RC. This is how we detect the envelope. Okay, and this envelope gives us the idea about the message signal. You note it down, then we'll take up the question on the next screen. Here we can see the first question. For an AM signal, we know the carrier frequency as well as the bandwidth of the message signal. Using which detector this signal can be demodulated? Which is the best detector among these three? Simple formula based question. Formula was written on the previous screen if you remember. So you may pause the video here and give it a quick try, and then we'll check the answer on the board. I hope you got the correct answer, which is detector 2. How? For that we should be remembering that condition 1 by fc should be much smaller than rc, should be much smaller than 1 by the bandwidth of the message signal. So putting the data here, 1 by fc, the carrier frequency is this 20 megahertz. So 1 by 20 into 10 to power 6 should be much smaller than 10 into 10 to power 3. Milli means 10 to power minus 3, and then 1 by 3 into 10 to power 3. The bandwidth of the message signal is 3 kilohertz. Do you agree? Computation is pretty simple. It comes out to be 5 into 10 to power minus 8. This comes out to be 10, and this comes out to be 3.3 into 10 to power minus 4. Do you agree with these things? Fine then. Now doing the calculation for the second detector, 1 by 20 into 10 to power 6 should be much less than 10 to power 3 into 10 to power minus 2 into 10 to power minus 6 should be much less than 1 by 3 into 10 to power 3. Simple mathematics is there. This comes out to be 5 into 10 to power minus 8. This becomes 10 to power minus 8 and 10 to power 3 means 10 to power minus 5, and this is 3.3 into 10 to power minus 4. Is it okay? Going further for the detector 3, 1 by 20 into 10 to power 6. R is 10 to power 4. C is 10 to power minus 12, and data here is 1 by 3 into 10 to power 3. Do you agree? Do the calculation. 5 into 10 to power minus 8. This data is 10 to power minus 8. 3.3 into 10 to power minus 4. Now if we check the data, the condition here is getting violated. Check here. Getting it? This is not a good detector. If we check for detector 3, the condition will get violated. Where? Here. 10 to power minus 8 and this data. This condition is getting violated here. So this is not a good detector. Here you can treat it the best detector among these 3. I hope you understand it. Note it down, then we'll be taking up the next question. Here is the second question and the last question of this video. It's a simple one. If you wish, you may give it a try, and then I'll be simplifying it. Okay, I'm starting the solution here. For simplicity, we imagine that received signal is AR cos of omega c plus omega m into t. According to the question, only upper sideband was transmitted, so we have received the upper sideband. Okay. Now, according to the question, at the receiving station, there is a facility of multiplying the received signal and the carrier signal. So after multiplication, this is the carrier, this is the received signal, and we are simplifying it. AR AC has been taken here. This is a format cos A cos B. Do you remember any formula? Any formula for cos A cos B? It is equal to 1 by 2 cos of A plus B plus cos of A minus B. Is it okay? Let's put up the data. This 2 comes here. Then we are left with cos of omega c plus omega m plus omega c plus cos of omega c plus omega m minus omega c, and t was lying here. Is it okay? This omega c is getting cancelled out. Actually, if we compare these two signals, its frequency is high because carrier frequency is always high. If we pass this entire signal through a low pass filter, only this signal will pass through that filter. Got it? So you will recover the signal, the message signal. Simple and easy question. I hope you enjoyed this video. This is all about this playlist. Stay awesome. See you again.